In the previous lecture, we looked at formulations as a way to convert a combinatorial problem into an integer program. Here, we're going to take a slightly different look at what a formulation is so that we can continue to think about integer programs and formulations geometrically. So first, let's go through the idea of what a formulation is. Here we have a set X of points in our feasible set. These can be feasible points from an integer program or a combinatorial problem. It doesn't really matter. The idea behind a formulation is that we're going to take some polyhedron, which is just a set of points defined by some set of linear constraints that's going to encapsulate this set X that we've circled. So, for example, if this is our set X in blue, some polyhedron that circles them is this thing that I'm drawing in pink or fuchsia. And this set P is a formulation because if I intersect this set P, this polyhedron, with all of the lattice points, the only set of lattice points I've circled are the ones in X. This is the idea behind a formulation, but we're going to have to get slightly more general and a little bit more particular about exactly what a polyhedron is. So this is going to be our formal definition of what a polyhedron is, or a formulation. A formulation is going to be a polyhedron. It's going to be defined by some set of linear constraints. And this polyhedron is going to be a formulation for some particular set X. And in this case, X is going to be a little bit more general. X is going to have some discrete lattice points from an integer program, but X also might contain some other points, some continuous variables that are going to be defined by any real numbers. So X is going to be something like a mixed integer program set of variables. Our polyhedron P is going to be a formulation for this set X if, whenever we intersect our polyhedron P with the set of vectors defined by Z and R over the proper dimensions, we get back our set X. Effectively, what this is saying is our polyhedron P is going to be a formulation when we look at the lattice points, Zn, it exactly circles the right lattice points. We've circled the lattice points that define X. And just to be precise, this space that we're looking at, this Z by R space, is going to be any set of vectors so that the first P entries are going to be integers and the next P to P plus N entries are going to be real numbers. So again, this formulation is going to be a polyhedron, and it's going to be a polyhedron that's going to circle the right lattice points. And in this case, we've defined a formulation so that we can circle lattice points and also have some real components that we don't have to circle exactly. Let's go back to a slightly more visual perspective and start looking at what are and aren't formulations. Here we have the simplest case, just some lattice points X. And I'm going to draw a formulation for X. And a formulation for X is just going to be any polyhedron that's going to circle all of the points and only the points inside of X. So down here, P is a formulation, where P is this shape defined by the green lines. We can draw some other polyhedrons that aren't going to be formulations. So sometimes we can have polyhedrons that are too small. So for example, this shape defined by the fuchsia, it's going to circle only lattice points in X, but it's not going to be circling enough of them. There's some points in X that aren't left out. So P is not a formulation. Conversely, if we have a polyhedron that's too large, let's say we try to circle more points than we should, then this P, the one drawn in red, is also not a formulation. This is the geometric definition of formulation, circling lattice points. We saw, though, that in our definition, we're going to have some cases where, in addition to lattice points, we're also going to have to consider continuous variables. On the other side, over here, we have a picture where we have variables that are both on a lattice and continuous variables. This is the way we should visualize them. Here we have a set x1, and x1 is going to be on the lattice points. x1 can only take the values 1, 2, and 3. But x2 is in any continuous space. X can be between 0 and 3. It can take values along this entire line. So in 2 dimensions, what we have is a series of lines, or line segments. In this case, our polyhedron has to circle exactly the lattice points, but also has to cut off x2 at exactly the right points. So here we have to be a little bit more careful with our drawing, and P, drawn in green here, is going to be a proper formulation. The reason it's going to be a proper formulation is because it circles exactly the points that are defined by x. In this case, I needed to just enclose these line segments and no others. So P is a formulation. When thinking about formulations, think about this geometrically. A formulation has to circle the proper lattice points, or the proper line segments. When we go back to our very complicated definition, this is the definition we'll have to work with for proofs. But when we think about things geometrically. Keep that in mind. The reason why we're moving to this more geometric, this more abstract definition of formulations is because throughout the course we're going to be comparing two formulations with each other. Here we have some geometry. I have a set X defined by these blue points. These blue points are the points in X. And I've drawn two formulations. They're both valid formulations. The green one circles all and only the points in X, and the red one circles all and only the points in X. So both P, the green one, and P, the red one, are formulations. But in some sense, P, the green one, is going to be a better formulation than the red one because it gets closer to the set X. It has less excess. It's smaller. We can formalize this idea, and we're going to continuously use this idea throughout the course. If we have P1 and P2, and they're both formulations, we can compare them. Specifically, if P1 is a subset of P2, a strict subset, then P1 is in some sense a better formulation. This is one way that we're going to compare formulations. Now let's suppose that I go ahead and I make the best formulation possible. The best formulation possible is going to be really just connecting the dots along this set X, these blue points. So this shape I'm drawing in magenta is going to be, in some ways, an ideal formulation. That is, this magenta P is the best possible P we can find. We can make this more rigorous by talking about a convex set or a convex hull. The convex hull of X, and let's be a little bit more precise about exactly what X is going to be a set of points, we'll say x1 through xn. The convex hull of X is going to be equal to all the points y such that two conditions are satisfied. Y is going to be a convex combination of the points in X, and this convex combination, or this linear combination, has to sum to 1. And all of these multipliers are going to be greater than or equal to 0. This set is the set of all convex combinations of points in X. So this is the convex hull. We're going to say that a formulation is ideal whenever it's equal to the convex hull. So when P is equal to the convex hull, P is ideal. The convex hull is going to be important in what follows. And geometrically, all the convex hull is this magenta where we've sort of connected the dots of the points on the exterior of X. Before moving on, we should say a little bit more about these ideal formulations. Looking back at our geometry, an ideal formulation seems to be the best possible way to have a formulation for an integer program. So why would we ever talk about using anything else? The problem is that ideal formulations are sometimes very hard to find. In fact, sometimes we can't even find an ideal formulation. And sometimes, when we can find ideal formulations, they're very large or complicated. They can be very large and very complicated. So although an ideal formulation is ideal in some geometric sense, because it circles all and only the right points, and in the best possible way, computationally, an ideal formulation might not be the best object to work with. We're going to see how ideal formulations and comparisons between formulations play out computationally all throughout the course.